Hello all, welcome back. So today we are going to discuss about semiconductors and we are going to take the topic on PN junction diode. So today we'll see how PN junction diode works and then how we get a PN junction diode, then moving on to what are the energy levels and then how we can understand the energy level in case of a PN junction diode, what about the Fermi levels, and then continuing into how the PN junction diode works plus the VI characteristics of the PN junction diode. So to start with, let us consider what are the discussions that we have done earlier. So what we have seen in the earlier video is that how the conduction takes place in a semiconductor. So it is due to two phenomena. First one is the drift drift current, second one is the diffusion current. So drift current is obtained by application of the electric field, and the diffusion current occurs with respect to the change in the concentration gradient. So that will give us the current flowing through a semiconductor, and the relations are given by these equations as you can see here, and along with that we have also discussed what is the Einstein relationship for a semiconductor. So the Einstein relationship is also given here in this equation at the end. So now moving on to a PN junction diode. So how it is formed? So to generate a PN junction diode, first we require a semiconductor wafer. So before going into how it is formed, first let us see the interesting topic of doping. So in simple words, doping is the intentional addition of impurity atoms into a pure semiconductor to change the number of the charge carriers inside it. So without doping, silicon is most useless for electronics. It conducts very little current, but with the right impurities, we can control how many electrons or holes are available, and that's what make all modern devices possible. So let's start with the basic idea. So a pure perfect crystal of a silicon is called an intrinsic semiconductor, as we can see here in this left hand side diagram. So here the number of electrons is equal to the number of holes, but this concentration is very low, not enough to run a real electronic circuit. So what we do? In this case, we add a small amount of impurities atoms into the silicon lattice. These atoms are either donate electrons or they create additional holes. So the beauty of the doping is that we need extremely tiny amount, even one impurity atom among the millions of silicon atoms can completely change the electrical behavior. So let's see what are n-type doping and p-type doping. So we add elements like phosphorus, arsenic and antimony atoms with 5 valence electrons, as you can see on the right hand side diagram where we have a phosphorus. So 4 of them bond with silicon and the fifth element remains free, as you can see this. So the electron concentration become much higher than the hole concentration. So now coming to p-type doping, we add element like boron, gallium or aluminum which contains 3 valence electrons, and it will create a missing electron or a hole in the bonding structure. As you can see here, this is a hole in the bonding structure. So this hole concentration increases. So now how this works? So suppose to fill up this hole, this electron will move from this position to this position, and at the same time there will be another hole created here. Then this electron may move further to another position, then again one hole will be created here. So like this we are generating more number of holes, and in case of pentavalent impurities we are generating or having an extra electron, and that will increase the number of electrons. So continuing with the idea of doping, so let us continue our discussion with the PN junction diode. So in PN junction diode we have both the impurities N type and P type, and combined is known as PN junction diode. So why PN junction diode? Because it contains holes and the terminal is known as P, and it contains electrons, the terminal is known as N, and there is a junction in between them, which due to which it is called as the PN junction. So as seen in the diagram, the PN junction diode is not actually looks like combination of two semiconductors. So it actually looks like this, as you can see here in this diagram. So to generate a PN junction diode, what we do is first we consider a n-type material, and then in that n-type material we dope with holes, and a layer of p-type or the dope holes get fused over the layer of the n-type material, and which generates the PN junction diode. But symbolically we represent it by this, as you can see here, and we consider it like formation of these two types, which we have p-type silicon, and on the right hand side we have n-type silicon. So now if we see the doping or inside the semiconductor, so it looks like something like this. If we can consider it in this format. So on the left hand side we have this circles representing the holes, and this small circles in green color are representing the electrons. So as soon as the doping is over, so what happens is there is no other force which is acting over them. So what the electrons will do, they will try to pair with the holes. So as you can see here, the electrons will get combined with the holes. So whenever this occurs, during this phenomenon, whenever an electron moves from n-type to p-type, it leaves a positive charge ion on the n side, and similarly after accepting the electron, the holes generate a negative charge ion in the p side. So these charges get aligned in the boundary. So due to the presence of these charges, when they overcome or when they fill the whole junction, then it forms a layer. So this layer, as we can see here, will not allow further flow of electrons or holes. So how that is possible? As we can see here, this layer is formed by negative charge ion, and this layer is formed by, on the right hand side we have positive charge ion. So since we have positive charge ions, so the holes cannot move in this direction, as they will repel. Similarly, as we are having the negative charge ion, so the electrons also cannot move, as they will repel across the junction. So this will create a layer which we call as the depletion layer. So this depletion layer, as soon as the combination or as soon as the doping is done with respect to the PN junction diode, then this layer is formed immediately, so which will prevent the further flow of holes or electrons. So this process will prohibit further movement. So that is why a PN junction diode doesn't conduct until and unless we are providing in any external force. Let us consider to exert a electric field here, which will form the drift current. So let us consider a biasing. So now what we are doing here, all the holes are connected to a negative terminal of the battery, and all the electrons are connected to the positive terminal of the battery. So this phenomenon will do what? It will attract all the holes away from the junction and all the electrons away from the junction. So this will increase the size of the depletion layer. So that means the movement of holes or electrons will not occur in this format, and we call it as reverse bias of the PN junction diode. Now considering the second option, where the holes are connected to the positive terminal and the electrons are connected to the negative terminal, in this combination, so what will happen is all the holes and the electrons will face a repulsive force, and they will try to move towards the depletion layer, as you can see here. So as we are increasing the forward bias or increasing the voltage in this forward bias, so what will happen? They will try to move towards the depletion layer, and they will in this this process, what will happen is the depletion layer will start shrinking. So after a period, what will happen? The depletion layer will get vanished and all the electrons will move towards the p side and all the holes will move towards the n side, leading to movement of the charge carriers. So in this way, what will happen? All the charge carriers will start moving from n to p and then further moving away, which will create the flow of electrons and finally which will lead to movement of the current. So as we already know, since the electrons are moving from n to p, so the current will be moving from p to n. That means conduction will take place. So to realize this, let us consider this demonstration which is shown here. So now here, as you can see, this is a PN junction diode, and this PN junction diode name is 1N4007. So in this PN junction diode, it is connected in forward bias. So as we can see here, the red wire represents the positive terminal, the black wire represents the negative terminal. So red wire is connected to the P side and black wire is connected to the N side. So how to identify this diode, that which side is P or which side is N? So we can identify that with the help of a mark which is present over the diode. So as you can see here, this is your PN junction diode, and in that there will be a mark, and that mark represents the N side or cathode side, and the other way around will be the P side or the anode side. So now the circuit is connected in forward bias condition, so that is why you can see the LED is glowing. So in this circuit we are having a diode, then a LED, and then a resistor, and then the resistor is connected to negative terminal, so the circuit is complete. So let's see how this works. So as you can see here, this is the forward bias. So if we change the position of the diode, that means if we change the position from P to N and N to P, then we are creating a reverse bias, and in that reverse bias the current is not flowing, which we have already discussed in our discussion, that whenever we are having a reverse bias, the movement of charge carrier doesn't happen, or that movement of charge carrier doesn't occur during this reverse bias condition. So that is what we have seen in the demonstration. So this is how PN junction diode works, and the formation of depletion layer and the forward biasing and reverse biasing of the PN junction diode. So next let us try to understand the formation of this depletion layer with respect to the energy band diagram. So now here, as we can see here, we have two semiconductor regions. On the left hand side, one semiconductor region, then on the right hand side we have another semiconductor region, and their energy levels. On the upper side we have the conduction band, on the lower side we have the valence band. So now in this case, the semiconductors are intrinsic, so that is why they have similar energy levels. So now if we start doping this, then what will happen is the conduction band in case of the N type will try to slightly shift down, and similarly the valence band will also slightly shift down in case of the N type semiconductor. So on the right hand side we have the N type semiconductor, and on the left hand side we have the P type semiconductor. So this change in the energy level is occurred because of the trivalent impurities exert lower forces on the outer space electrons, and the lower forces mean that electron orbits are slightly larger and have a greater energy. So this will create this change in the energy bands, and while this is happening, at the same time the upper layer of the conduction band of the N type and the lower layer of the conduction band of the P type will remain in the same energy level, so which will make the electrons to move from N type to the P type. So this will allow the free movement of the electrons. So now as the electrons move from N type to P type, they will lose energy and they will fall down towards the valence band with the holes. So as we have seen that the electrons are moving from conduction band of the N type to the P type, and at the same time the depletion layer also start forming, so which will get created in this format, and slowly or gradually as the electrons are moving or the holes are accepting the electrons, the charge positive and negative charges are getting developed at the boundary. So in this energy level, what will happen is the energy level will try to shift downward. So as you can see here, so after a certain period, what will happen is the lower energy band of the P side and the upper energy band of the conduction band of the N side, they will try to get over a same level, and similarly that will happen with respect to the valence band. So what we want to mean is the lower level of this conduction band, that is the P side conduction band, and the upper level of this conduction band, that is the N side conduction band, now they are aligned in a same line. So whenever this is happening, automatically the electrons stop moving from the conduction band of the N type to the conduction band of the P type, because now in this case they have to move further and they doesn't have that much of energy for the movement. So this will create or generate the formation of the depletion layer. So in energy format we can represent it like this. So now if we see at the same time the difference between the conduction band and the valence bands are remaining same in case of both N type and P type semiconductor, that is a PN junction diode, and the Fermi level, as we already know, the intrinsic Fermi level lies in the middle, so it is also in the middle. So now if we see the energy levels and then do the proper nomenclature of them, so we will find it as this is the EF given by this yellow line, which is representing the Fermi level. So this Fermi level, as we already know, in case of p-type semiconductor, the Fermi level is near the valence band, and in case of n-type semiconductor, the Fermi level is near the conduction band. So it is happening and it is valid in this diagram. And we have this ECP is the lower region of the conduction band in case of p-type, and this is the ECN, which is the lower region of the conduction band in case of n-type. So the P and N represents the sides, that means on P side, either it is on P side or N side. Now here similarly we have EVP and EVN, and the difference between valence band and the intrinsic layer is given by half of the EG, where EG is the band gap energy. So here if we determine the total shift, so the total shift will be E naught equals to E1 plus E2, where E1 and E2 are given as ECP minus ECN plus EVP minus EVN, right? So this is how the energy level of PN junction diode is formed, and this will remain same until and unless we are providing any external force. So this represents the energy band diagram of the PN junction diode. So now moving forward, so now talking about the depletion layer. So in the depletion layer, if we see different properties, then in a PN junction diode we have the depletion layer, and the depletion layer positive charge ions are on the N side and the negative charge ion on the P side, that we have already discussed. Now if we see the carrier concentration, so the carrier concentration of holes will be higher on P side, then it will slightly getting down, or it will be less in the junction, and then it will be minimum in the N side. And similarly electrons are maximum on the N side and gradually decreases towards the P side. Now if we determine the space charge density, so now these are negatively charged, so we will have a negative charge here, and these are positively charged on the depletion layer of N side, so it is positively charged. So now if we measure the electric field, so the electric field will be the difference between this potential. So that difference will be obviously in the negative direction, because this will create a voltage which will oppose the movement of electrons. So that is why we have in a negative direction, and this represents the electric field, and this value is given as 0.7 for silicon and 0.3 for the germanium semiconductors. Now similarly, if we check the voltage will be given by this format. It is negative in P side and it is positive in the N side. So these are the various properties of the depletion region as we have discussed in this slide. So now moving further, so how a PN junction diode works, as you can see here, there is an animation which we have taken from this makeagif.com. So as you can see here, this is the forward bias where anode side or P side is connected to the positive terminal, and the N side or the cathode side is connected to the negative terminal, and the movement of charge carriers are happening. And initially, as you can see here at the starting of the video, we have a depletion layer, and that depletion layer is eliminated with application of higher voltage. So that voltage uh, which is required for overcome this depletion layer is given as or called as the threshold voltage or the knee voltage. So which, as you can see here in this diagram, so initially whenever we are below that knee voltage, then there is no movement or very less movement of current. But as we are overcoming this knee voltage, then gradually the current will increase and it will take a linear format, like in case of Ohm's law. So this is the forward bias characteristics. So as you can see here, this is the forward voltage, this is the forward current. So this is the representation of the characteristics of the diode in forward bias. Similarly, if we see the reverse bias case, as you can see on the right hand side animation, so the depletion layer increases and there is no further movement of electrons or holes. But as we already know, there are minority charge carriers in P type and N type. So for them, this polarity of the supply behaves as the forward bias condition, and there will be very little amount of current flowing through the diode. So that is why, as you can see here in this graph, in the reverse bias, so this is the reverse bias voltage, this is the reverse bias current. Since the polarity is opposite, but providing it as a negative sign. So now, as you can see here, this also in this region also we are having some amount of current, but the very difference between the forward bias and the reverse bias is in the forward bias we have milliampere range of current, and in the reverse bias we have microampere range of current. That means the current in the reverse bias case is very small in comparison with the forward bias. Now, as you can see here, there is a sharp increase in the current. So this sharp increase is occurred when we are providing very high amount of reverse bias voltage that will create a high collision of the holes and electrons, and which will finally generate a breakdown. So that breakdown is known as the avalanche breakdown, where the collision of the electrons and holes or the charge carrier takes place, and that collision will rupture the covalent bond, which will generate more number of free electrons and holes. So finally we will have more, as we have more free number of electrons and holes, the conduction will take place, and that is why, as you can see here, high amount of current is flowing, but at the same time it will disrupt the PN junction diode. But as you can see here in this graph, there is another point is mentioned, that Zener breakdown. So what is Zener breakdown? Zener breakdown occurs in Zener diode. So in Zener diode, the case is slightly different. They are highly doped, and in that what will happen after a breakdown voltage, which is given as Vz. So as we reach this region, the Zener diode will start conducting. So why it start conducting? Because at that time the breakdown will take place and the charge carrier will start moving. So this diode, the Zener diode, is used for working in the reverse bias condition only. So it is not that we cannot work in the forward bias, we can definitely work in the forward bias, but basically the application of Zener diode is for the working in the reverse bias condition. So in this case, what we can do is we can take help of this property and generate voltage regulators. That means suppose if we want to control the voltage of a device, that means suppose at the input we are getting voltage around of 12 volt, and in the circuit we do not require 12 volt. So what we can do, we can put a voltage regulator. That regulator can control the voltage and make it constant at a particular level. Say for example, if you want to stop the voltage or make the voltage constant at 5 volts, so that can be done. So what we have to do is we have to just put a Zener diode which reverse bias breakdown voltage is 5 volt, and putting that Zener diode in a reverse bias condition will help us to maintain the voltage at 5 volt. So now in order to understand that, so let us take help of an visualization at practical circuit. So as you can see here, this is a Zener diode. In the right hand side you can see the bigger format of the circuit. So here we have, this is the Zener diode. It is connected in the reverse bias in this case, and in this case it is connected in the forward bias. So let's see how it works, and I will explain it as the video progresses. So in this, as you can see here, it is connected in forward bias condition. We have N terminal over here, P terminal over here. So the connection is in forward bias. So that is why the light is glowing. And we can see the voltage is around 4 volts, 4.5 volts. Now when we change the position of the diode, there is no movement of charges and the LED is off. And at the same time, if we increase the reverse bias voltage, there will be current movement. So as you can see here, the current is increasing. So let us consider the second diagram, which will give it a more clearer view. As you can see here, the output voltage is 4.15. There is no glow in the LED. Now if we increase the voltage, so as you can see the voltage is increasing, it is showing in the multimeter. So as we are increasing the voltage, we are reaching now 6 volts, the LED glows. That means in reverse bias condition, the Zener diode works. So this is how a PN diode and a Zener diode will operate. So similarly, we have different other types of diode which are known as various diodes. Like as you can see, the glowing light, as you can see here, is known as LED, which is also a diode, and the full form of LED is light emitting diode. So it will emit a light whenever the current passes. So it is doing its property there, as we can see. So today in our discussion, we have practically seen three diodes. One is PN diode, second one is Zener diode, and also third one is the LED. So similarly, there are other diodes also which have different other properties which we can use depending on our applications as we require. So our class today started with the PN junction diode. So how PN junction diode is formed, how the doping is done, and as we dope the semiconductor, then how the depletion layer is formed, what is the property of the depletion layer, and how the depletion layer is formed with respect to the energy levels, what is the shifts, and how the depletion layer prohibits the movement of electrons and holes. That also we have seen. And then later we have seen how after application of the electric field, the diode starts conducting. And we have seen that there are two possibilities. One is forward bias and second one is the reverse bias. In the forward bias, we connect P terminal to the positive of the battery and N terminal to the negative of the battery. And in the reverse bias, we just shift the position. That means P is connected to negative and N is connected to the positive terminal. And in case of PN junction diode, in reverse bias, there is no movement of electrons or holes. And if we increase the reverse bias voltage to a higher extent, then breakdown of the diode will take place, and the process is known as avalanche breakdown. And after that, the diode becomes inoperational and the diode gets damaged. At the same time, we have another diode which is known as Zener diode, which is made for operating in the reverse bias condition only. And in reverse bias condition, as we have seen in the demonstration videos also, that as we are increasing the voltage in the reverse bias, the diode starts conducting. So this is all about PN junction diode, how it works, and the properties of PN junction diode and its characteristics. So I hope you have understood why PN junction diode doesn't work below 0.7 volts in case of silicon semiconductor, and how PN junction diode doesn't work in the reverse bias, and also we have seen that the Zener diode works in the reverse bias condition. So with this, let us stop our discussion here, and so if you have any queries, you can put it in the comments and let me know what are the other points that we need to cover, and we'll try to incorporate that in our next class. So if you find the videos useful, then do like, share and subscribe. Thank you.